Okay, so now we're going to talk about Le Chateliers principle and how it relates to shifts in equilibrium as we change pressure. And so the first thing I'll say is this is only going to work on equilibrium systems where there's at least one gas present, one gas species in our equilibria. So if it's all, aqueous, liquid and solid, stuff like that, we're not going to see it. There's going to be no effect from changing pressure, or negligible. We'll say negligible. So we're not going to worry about it. But if there's gases, for example, we'll stick with our formation of ammonia here, then it's going to shift. If we increase pressure, equilibrium is going to shift towards the side with the least moles of gas, because it's going to favor pushing these together and using these. These are going to take up less space. Remember, PV equals nRT. It doesn't matter what the gas species is, just the number of moles. And so the side with the least moles is going to relieve the stress the most of the increased pressure. The molecules are going to be a little bit more room to roam. They're not going to be bumping into each other as much. So the low side's favored. So this is kind of just like an overarching argument, kind of a logical, poorly phrased argument by me right now, I'll be honest. I don't feel like I'm making it very clear, but we'll do the math in a second. So just look at it, we've got 4 moles on the left, we got 2 moles on the right. So if we only had NH3 in this situation, it would experience half the pressure versus the left-hand side. If we had this set up, we'd have 4 moles of gas. It was all that. So we can cut the number of moles of gas in half by just completely shifting to the right. Now that doesn't happen necessarily. You don't get a complete shift unless you really crank the pressure and you get a near complete shift. But it's going to favor this side more, because as you compress it, it's going to favor, cutting down its commitment on the number of molecules of gas floating around. And to do that, it's whatever side just has the least moles present. Now, if they're equal, if we had something like 3 and 3, then there would be no change by adjusting pressure. So you have to have an unequal number of moles, and it's just going to favor the side with the least moles. Now, if you drop pressure, it'll do the opposite. It'll favor the side with more moles. And that's total pressure. I want to be clear. So if we're talking about changing the partial pressure of just one product or reactant or whatever, like if we just up the partial pressure of N2, that means we just added more N2. We've upped its concentration, and so it's going to shift right. Just like if we talked about in the last video, if we mess with concentration, well, if we mess with individual partial pressures, exact same scenario. But if we change the total pressure, if we compress the whole system together at once, we're not adding or removing any particular gas, we're just making them all squeeze into a smaller space, it's going to favor whatever side has the least moles of gas on it. So that's kind of just the, like I said, the overarching argument. The mathematical argument, well, we're going to start with our Q value for partial pressures. We write that out, and what we're going to do is we'll say we cut the volume in half. So our pressure is going to double. So all of our partial pressures are going to double right along with it. Okay, so all the pieces double, the whole doubles. That's what we're saying. So our Q is, partial pressure of product squared over partial pressure of reactant and reactant cubed, so H2 cubed. Okay, and if I double my partial pressures, all of them, that's just 2 times whatever it was before I cut the volume in half. So my equilibrium pressure, that's what that is. All right, and so I have 2 times this pressure, 2 times this pressure, 2 times this pressure, and all my exponents go on the outside. So if I factor out those exponents, this ends up being 4 times the pressure of NH3 squared at equilibrium. Underneath we get 2 times 2 cubed, which is 8, so that's 16, and then these partial pressures are all the equilibrium values, so that's Kp. And so what we did is we actually cut our value to 1/4 of its equilibrium value. So Q is less than Kp. Hungry alligator was going the wrong way. So Kp is larger, about, 4 times larger than Q right now. And so that means that we are not at equilibrium, so it has to shift. And it's going to shift towards products, because if Q is small, then we need more products to make it larger to reach equilibrium, less reactants. So that's what's going to happen. So that's kind of the mathematical explanation of what's going on. It gets a little crazy. And so again, this just means that this is the equilibrium pressure. And whatever we are in the moment was double that pressure. And that's all I did. I just substituted in 2 times the equilibrium pressure for all my pressures, and I factored out the exponents. And we come out with 4/16 times Kp, which is 1/4 Kp. That's what we're looking at. But again, all it boils down to is whatever side has less moles of gas will be favored at high pressures. And it will not be favored, the other side will be favored at low pressures. So it just depends on what our expression is. So that is how pressure affects our, that is how changing pressure affects our response at equilibrium. How does it shift to equilibrium? How does it shift off of equilibrium? And then what does it need to do to return? That's what we're looking at. So what is the stress and what does it do to relieve that stress? All right, so next we're going to talk about temperature and then catalysts.